Hey everybody, this is Mr. C, and this is Ready, Set, Go, Unit 1, Lesson 6. So question number 1 asks, what's the smallest fraction of a full circle that the wagon wheel needs to turn in order to appear the very same as it does now? So in other words, how far do we need to turn it? What fraction of this circle? Well, it looks like our circle is being divided into 1, 2, 3, 4, 5, 6, 7, 8. So we would have to divide it, spin it 1/8 of a rotation, or 1/8 of a circle, which would be 45 degrees. On the next shape, this propeller type shape thing, this has got 5 little arms here, so a full circle is being split into fifths, which would be 72 degrees to turn. On this Ferris wheel, we need to count all of the arms of this one, so I'm putting a little mark here so I know where I started at. So this is 1, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we need to figure out, that'd be 1/18 of a full circle, which, if we take 360 divided by 18, that gives us 20 degrees. Okay, moving on to our set. Draw the lines of symmetry for each polygon. Fill in the table, including expression for the number of lines of symmetry in an n-sided polygon. Okay, so we have done this in the previous lesson. Our triangle has 3 lines of symmetry, and every odd-shaped one goes through vertex through midpoint. So the pentagon has 5, and then the 7-sided heptagon, every vertex across to the vertex on the other, across to the midpoint on every side. Like so. There we go. There's 7. On the even number shape, so we can actually write these down. So the 3 has 3, 5 has 5, and the 7 had 7. On the even numbered shapes, we have half of the lines of symmetry are going from midpoint to midpoint. And the other half are going through the diagonals. A little bit better. So that would be 4 for the square. And then for the hexagon, 3 of those going from midpoint to midpoint. And then 3 diagonal lines of symmetry. So 6. And then finally for the octagon, we would have 4 going from midpoint to midpoint, and then 4 going through the diagonals for a grand total of 8. And it seems that the number of sides matches the number of lines of symmetry. So if you have n sides, you are going to have n number of lines of symmetry. On the next one, they want us to draw the number of draw the diagonals and count them up. So on a triangle, there are no diagonals. So that one's easy. There are 0 diagonals. Oops. 0 diagonals on a triangle. The square has 2. Then we get to the pentagon. And if we start here, we have 1 diagonal, and then another diagonal, and that's all we could draw from that point. So then we move to the next vertex, and I can see that that one's also going to have 2 diagonals. So it looks like each vertex is going to have 2 diagonals going to it. So and this one already has 1, so I got to draw 1 more. And then everyone has 2 diagonals, so that is a grand total of 5. Okay. Then to the hexagon. Maybe we'll start at this vertex and draw diagonals. So got 1 going over here, 1 going over here, 1 going over here. So 3 coming from that vertex. So each one should have 3 diagonals. So there's 1, 2, 3. Okay, done with those 2 vertices. Over here, we already have 1, so I need 2 more. There's 1, and then there's 3. Then we get down to this point right here. There's already 2, so there's just 1 more that needs to be drawn. And now I can see that every vertex has 3 diagonals connected to it. So grand total of 9 diagonals. Then to the heptagon, start at this vertex here. There's 1, 2, 3, 4 diagonals. And I'll move to this next one. So I'm going to keep track of this so I can count it. So we had 4 that I've drawn so far. Then another 4, 2, 3, 4. And then this point already has 1 diagonal, so I got to draw 3 more. There's 1, 2, 3. And then this point already has 2, so I need to draw 2 more. There's 1, 2. And then this point already has 3, so I need 1 more. And now every point has 4 diagonals connected to it. So totaling these all up, 4, 4, 8, 11, 13, 14. Okay. And then the last one, the octagon. Maybe we start with this point right here. We draw 1 diagonal, 2 diagonals, 3 diagonals, 4 diagonals, 5 diagonals. So each vertex is going to have 5 diagonals coming out of it. So there's our first point. Let's go over here. We'll draw another 5 from that point. So over here, 5, or sorry, 1, 2, 3, 4, and 5. Moving along, this vertex, we already got 1 diagonal, so I got to draw 4 more. 2, 3, and 4. So I drew 4 new ones. At this point we have 2 already coming in, so I gotta draw 3 more. So there's 1, 2. That one didn't look too good. 3. And this one we have 3 already, so I need to draw 2 more. So there's 1 and 2. And here's the last one. We have 4 already, so there's just 1 more diagonal to draw. So total these up: 10, 14, 17, 19, and 20. Okay, so we can fill in our table. So 5 and 9, and 14, then 20. And the pattern that I'm seeing here is that starting at 0, we did +2, then +3, then +4, +5, then +6. So not a linear expression. If we're trying to find an expression for this, we could use a recursive expression. So we could say n, so it would be a function of number size would be equal to n minus 1 add. Actually, let me try it a different way. Let's try this. Let's use Desmos. Maybe we'll just come up with an explicit formula. Okay. So I'm going to go ahead and create a table here. This is kind of cheating, but that's okay. Okay, so first one had 3 sides and 0, and then 4, and went all the way up to 8. So we had 2, and 5, 9, 14, and 20. So this looks like a quadratic. So I'm going to go ahead and do a quadratic regression here, just so I can cheat and get my formula. So we'll ask Desmos to approximate. Oops. So AX1 plus BX1 plus C. Okay. Didn't. Oh, that's why. I need to make that a x1 squared. There we go. So there's my quadratic. Fits nice and perfectly. So A is 1/2, B is -3/2, and C equals 0. So my explicit formula would be 1/2 n squared plus, oops, or not plus, minus 3/2 n. This last part was a little bit advanced, just going back to some algebra. There are other ways, algebraic ways, we could have come up with this quadratic formula. Okay. Number 6, find the angles of rotation that will carry the 12-sided polygon onto itself. So for this one, we're going to take 360 and divide it by 12. And that gives us 30 degrees, so every 30 degrees we're going to have rotational symmetry. So 30, 60 degrees, 90, 120, 150, 180, 210, 240, 270, 300, and 330. And we'll stop there because the next one will be 360. What are the angles of rotation for a 20 gon? And how many lines of symmetry? So same thing, we'll take 360 divided by 20, and that is going to be 18. So every 18 we would have. So it would be 18 degrees, 36 degrees. So let's 18 plus 18 plus 18 plus 18. So 54, 72. Plus 18, that'd be 90. 108 degrees. One 26, 144, 162, 180, 198. The next one. Oops. 216, 234. 252, 270, 288 would be the next one. 306, 324, 342, and that will be the last one. Okay. What are the angles of rotation for a 15 gon? Oh, actually, we forgot to answer the question. How many lines of symmetry? Lines of reflection. This one's a little bit easier. There are going to be 20 lines of symmetry. What are the angles of rotation for a 15 gon? We'll take 360 divided by 15. So that would be 24. So every 24 degrees. So 24, 48, 72, 96, 120, 144, 168, 192. Let's see. 216 for the next one. 240. 264. 288. 312. 336. And then the next one would be 360. Okay. And then 15 sides, 15 lines of symmetry. A really regular polygon has rotational symmetry for an angle of 18. How many sides does it have? Well, where have we seen 18 degrees for rotational symmetry? Right there in number 7. So a 20 gone. Well, there are others that would work. So if that works for a 20 gone, imagine if we had a 40 gone, we would be hitting at every 9 degrees. So 20 gone or a 40 gone, would also work, and any multiple of 20 would also be possible. Okay. Multiples of 20 gone. A regular polygon has a rotational symmetry of 20 degrees. How many sides does it have? So one way to solve this is if we did, well, actually, it seems like we answered a similar question up at the start. And looks like in number 3, an 18-sided shape would hit every 20 degrees, so 18. And any multiple. Will also work. Alright, question number 11. 11 through 13, we're doing some reflections here. So we need those perpendicular slopes. So I need to find some good grid points. So it looks like our line of reflection has a slope of positive 3/1. So our reflected points need to have a slope of negative 1/3. So there's one step of negative 1/3. And there is where A prime is going to be. For number Number 12. Find some good grid points. So right here, and looks like right here. So our line of reflection has a slope of negative 4 over 1. So our reflected corresponding points need to have a positive 1/4 slope. So up 1 over 4, up 1 over 4. Now this one's a little tricky because we're hitting our line of reflection not exactly on our on full steps here. So to kind of help us figure out where our point needs to be, so there's our coordinate point. And hitting our line of reflection went a total up to over 1, 2, 3, 4, 5, about 4, 5.5. So we might just have to estimate here, keeping that same distance. Just because we don't have clean steps that we can do. So I'm using my ruler here. It's 1, 2, 3 major lines in 1 quarter there. So that would be 1, 2, 3 and a quarter, so right about there. That's where A prime is going to be. So no good, easy, clean way to find where A prime is. We're going to have to just kind of measure it so that we're equidistant from our line of reflection. Okay, let's see if we can do this nice clean one here. So our line of reflection has a slope of positive 1/2. So our reflected points are going to have slopes of negative 2 over 1. So if we take B, yep, we're not going to hit cleanly on these ones either. So that's okay. We can draw the line. So that we are perpendicular to our line of reflection. And then we can just measure distances and make sure that we're equidistant to our line of reflection. Alright, there's where B prime should be. So just taking my ruler and measuring. Right about there, we're off our grid. Somewhere right about here. Okay. Not perfectly precise, but definitely got the right slopes between our line of reflection and our corresponding points, which is the important thing. And that takes us to question number 14. Get some more of these reflections. So again, we're going to check our line of reflection. This is a little bit easier because this is a slope of -1 for our line of reflection. So our new slopes are going to be equal to +1. So that's going to be a lot easier to graph. We had 3, 1, 2, 3, 4 steps. So we'll do 1, 2, 3, 4 steps. That's where A prime is going to end up. D, 1, 2, 3, 4, 5 steps for D. So 1, 2, 3, 4, 5 steps. There is D prime. 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, and 5. There is B prime. And I'm going to use, just knowing that C and A are across from each other, I can use that knowledge to figure out where C prime is going to go right there. And now I can connect my dots. Okay, there's my reflected shape. Okay. For 15, we have this reflection, but we need to figure out where the line of reflection is. So I'm going to go ahead and connect my corresponding points. And then I'm going to find the midpoint right in between there. Okay. So there's halfway between x and x prime, between y and y prime. There's the midpoint. So my line of reflection, going to go right through those. And I know that works because those slopes have a -1 slope, and my line of reflection has a positive 1/1 slope. And finally 16, same thing. We'll connect our line, our corresponding points. Those two right there. And halfway between T and T prime, there's that midpoint between Q and Q prime. That midpoint, that means we have a nice vertical line of reflection, just like so. And that's the end of this Ready, Set, Go.